Hello everyone. This video covers sections 1.3 and 2.1 from the book. Before we go there, let's just review what we did last time. Last time we talked about the two sources of error in numerical analysis. The first one is round of error, and that's technically due to the finite digit arithmetic. So this depends on whatever computer you're using. You cannot change them. And remember, there is technically two kinds here: rounding error, which is definitely due to the computer, and then the chopping error, which is where you will decide to stop. The second type of error is truncation error, and that is related to whatever method you're using. For example, remember that e to the x, this is from calculus 2, the Maclaurin series. This is the exact formula, which will be 1 plus x squared over 2, and so forth. So if you decide to use this part only, then this will be considered an error. So this will be like the truncation error. We'll get into a lot of details about that later, but that's what this means. Now let's look into algorithms and conversions. Algorithms is the main thing we want to do in this class. So algorithms are just instructions on how to solve a specific problem. There's technically three types or three things that can happen. The algorithm could be stable, which is what we want, unstable, which definitely you don't want, and conditionally stable. Okay. Stable means that a small change in the initial conditions of initial data produces a small change in the final result. So that's what stable means. And unstable pretty much means is not stable. Or in other words, if you make a small change at the beginning, the answer at the end changes a lot, which is a bad thing. And then there's a kind of special case, conditionally stable, in which some algorithms are stable just for some specific initial conditions. So this is stable for very specific initial data. And why is initial data or initial conditions important? Well, remember, pretty much an algorithm is going to be a sequence of steps. You will have like step 1, step 2, and so forth all the way to step n. So you have to start somewhere. So this is going to be the initial condition. So this is something very important that you probably didn't have to worry about before. Without the initial condition, the computer cannot do anything because you need to start somewhere. And stable means if you start with a number here and you get a close answer, and then you make a small change, the answer is going to be very close to the other answer too. So the difference will be very small. Unstable means that if you start, let's say, with A and you get the answer, and you change it to B and you get something completely different, that's an unstable algorithm, which means it will work only for like one case, which is not a good method. All right, so let's get a little more specific on this. So let's look to definition 1.17. Suppose that E0 denotes the initial error, which what I was talking about, at some stage in the calculations, and En represents the magnitude of the error after n subsequent operations. So if En is a constant times n times the initial error, then we say that the gross error And this is one of the main issues in numerical analysis. The grow error is going to be linear. So for example, let's say the E0, the initial error is equals to 0.2. And then if E10 after 10 steps, this is equals to like 5 times 10 times 0.2, this will be considered linear. And pretty much no matter what we do, we're gonna get always at least a linear error, so you cannot avoid this. So therefore, if this one is small, this will be small, which means the error is growing linearly, and you just have to figure out how to control it. So no matter what, we're gonna get something like this. So this is what we want to get. This one you don't want to get. Exponential means that the error increases exponentially. So using the same terminology, this will be, let's say, e to the n. And if c was equals to 5 for a constant, it will be 5 to the 10 times 0.2, which is, this is a huge number. So therefore, this is not good. So if the error is exponential, then the method is not the best. You need to find something better right away. And in some sense, you can say that this is stable and this is unstable, to follow these things we were taking here. All right, so now let's talk about ratio convergence, which is a very, very important thing to remember. You actually saw some of these things in also Calculus 1 and Calculus 2, but now we're going to be very specific here. So definition 1.a, suppose the Bn is a sequence known to converge to 0. So this one has to converge to 0. There is a lot of those sequences. And alpha n converges to alpha. So this is the approximation to this. So now if a positive constant k exists, where the absolute error is less than the constant times this sequence, then we say the alpha n converges to alpha at a rate of order big of, this is called big of, b of n, and it's indicated by this. So this and this means the same thing, okay? Now before we do this example, let's try something easier. So let's say that we have alpha n, and this is one of the examples in the book, is equals to this. Clearly you can see that this converges to 0. So then this will be alpha. So therefore, if we do the absolute value of alpha n minus alpha, this gives you n plus 1 over n squared minus 0. Since n is positive, this is the same thing as n plus 1 over n squared. Now this is less than or equals to n plus n over n squared. How do we get this n? Well, since n, the values for n are 1, 2, 3, and so forth, that means the 1 is always less than or equals to n. So then this is equals to 2n over n squared, which is equals to just 2 times 1 over n. Let me erase this part here. So therefore here, that implies the Bn or beta n is equals to 1 over n, and the rate of convergence is 1 over n, big O 1 over n. Or in other words, you can say that alpha n is equals to 0 plus big O of 1 over n. And that's it. All right, so now let's try this example. And again, most of these examples come from from calculus. Of course, in calculus, they didn't ask you to find the rate of convergence. They just ask you to check that they converge, but it's the same idea. Right, so here, notice the, okay, using pre-calculus, the ln of n plus 1 minus ln of n is the same thing as ln of n plus 1 over n, which is the same thing as ln of 1 plus 1 over n. And this will be defined to be alpha n. Clearly here alpha is equals to 0 because the limit is 0, so this converges to 0. So therefore, what we want is alpha n minus alpha to be bounded by something. So in our case, this will be ln of 1 plus 1 over n in absolute value minus 0, which is still just ln. Now, this is the part where you need an identity, and if you don't remember this or you haven't seen this before, well, this is your lucky day. You will see it right now. So recall that ln of 1 plus x is less than equals to the absolute value of x for x between 0 and 1. So this is not always true. It's only true between 0 and 1. But like I just said a few minutes ago, the value for n is 1, 2, 3, 4, 5. So this part is always less than or equals to 1. So therefore, using this identity, this is less than 1 over n all the time. And you can say times 1. So therefore, the value of the constant will be 1. So therefore, that implies that Bn will be 1 over n, or the ln of 1 plus 1 over n is equals to 0, which is the limit plus big of 1 over n. Right, let's look to the next example, and this one looks a little more tricky. You try to do the inequality, it could be more messy. So therefore, instead, and this is where calculus comes to the rescue again, remember that cosine x in Taylor series was defined to be the sum from n equals to 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So recall this. Therefore, you expand this will be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial and so forth. Notice that in the second problem, the limit is as h goes to 0, not as n goes to infinity. And n is the one that is defined for the sequences. So you need to watch out for that. So this is what we have so far. We have 1 minus cosine h over h, which technically you could say that now that's alpha h, and alpha is still 0 in our case. Now if we use this expansion, we have the following: 1 minus cosine, but cosine h is going to be 1 minus h squared over 2 plus h to the 4 over 4 factorial minus and so forth. And we're dividing everything here by h. Here you can see that this cancel. You'll end up with just h over 2 plus h to the 4 over 4 factorial and so forth. Actually, this is h cubed. Now the only part that we had to worry about is this one, so this is doesn't matter. So therefore, you can see right away that 1 minus cosine h over h will be 0 plus h over 2, or we can say 1 minus cosine h over h is going to be 0 plus big O of h. So for problems involving sine and cosine or even tangent inverse e to the x, it's better to use the Taylor expansion to try to figure out the rate of convergence. So you have a few of those on the homework, so you should try to do it this way, because it's not that obvious to just use the inequalities. All right, let's go to chapter 2 now. And the main purpose of chapter 2 is how to find solution to this problem, or the rule finding problem. Specifically in chapter 2, we're gonna focus on solutions to solutions of equations, or to equations in one variable. Okay, so notice how it doesn't say linear equations. It could be any equation in one variable. Like it could be something as simple as this, which my cat can do, or something as complicated as this. Yeah, so it's just one variable. There are like 4 or 5 different methods we're going to look into in chapter 2. The first one is called the bisection method, which is the most basic one. And bi, remember, means 2. So the idea of the bisection method is very simple. And this is what you're going to do. You're going to first pick 2 points, A1 and B1. So the one will be positive and one will be negative. And remember, by the intermediate value theorem, that means that if it changes from negative to positive, it has to be 0 at some point. So first we're going to start with 2 points, A1 and B1, where you check that this is positive, this is negative, or this is positive, this is negative. They just have to have opposite signs. Then you're gonna, the first step, you're gonna do to pick P1. P1 is just the midpoint between these two, so it's the midpoint. This is what is called a pseudocode. So this is the algorithm, but this is not the actual MATLAB code. So this is a pseudocode which tells you how the process is gonna work. So you still have to write it in the right syntax, and we're gonna do that on Friday on the MATLAB part of the class. But this tells you exactly what you're supposed to do. So here it is. So first you check that this and this have opposite signs. So the first part you do is you find P1, which is the midpoint of those two. If you get 0, then you're done, which will be great if it happens after one step. If that's not the case, then you evaluate this value, and now this one also has to be either positive or negative itself. So if FP1 has the same sign as, has to have the same sign as either this one or this one. If these two have the same sign, okay, then that means that P now has to be in the other side. So this is it's very simple like this, look. So you have, let's say this is positive, this is negative. You find the midpoint, and if the midpoint is positive, well, that means that the answer is not here. It has to be here, and you keep doing the same thing. You find another midpoint, and if this is still positive, well, the answer cannot be here, now it has to be here. And you just keep going until you get closer to the answer. Now, what do I mean by closer? Well, you need to have a way to stop at some point, so therefore it's a good practice, okay, to set an upper bound for the number of iterations. So there's technically several ways to stop the code. You can say I'm gonna do this 1,000 times, and if it doesn't work, I'll just stop there. Or I'm gonna stop this until the uh, tolerance is like 1%, 2%, and so forth. So we need to have a way to stop. Usually these are the three stopping criterions. The first one says the absolute error between two previous approximations is less than some epsilon, or the relative error is less than epsilon, or if the function evaluated at approximation is less than epsilon. So you need to use at least one of these three. Well, let's see how this works. Let's do an example. So the question says, use the bisection method to approximate the square root of 4. Well, we all know that the square root of 4 is 2, okay? So that gives you a good way to know where you're going. But you need to have a polynomial, so therefore f of x is going to be x squared minus 4. Why? Because if x squared minus 4 is equals to 0, that means that x is equals to square is equals to 4, or x equals to plus or minus square root of 4, or plus or minus 2. So we know one of the answers is 2. So let's pick a1 to be, let's say, 0, and b1 to be 3. Now f of a1, which is the same thing as f of 0, is 0 squared minus 4, which is negative 4. Clearly this is negative. And f of b1 is the same thing as f of 3, which is 3 squared minus 4, which is 5. 9 minus 4 is 5, which is clearly positive. So therefore from here, p1 is going to be a1 plus b1 divided by 2. So it will be 0 plus 3 divided by 2, which is 1.5. All right, so now we find f of p1, which is the same thing as f of 1.5. And this is 1.5 squared minus 4, which is a negative 1.75. So this is negative. All right, so here, the square root of 4, we're going to call it p, whatever the value is. Now, since this is negative, and a1 is also negative, that means that the new value for a is going to be 1.5. So the answer has to be now between 1.5 and 3. So from here now we have that a2 has to be now 1.5, and b2 is going to stay as 3. Or that the solution p is going to be between 1.5 and 3. Alright, so we just follow the process. Again, this is very straightforward. So now p2 is going to be a2 plus b2 divided by 2. So it will be 1.5 plus 3 divided by 2, which is equals to 2.25. And check again, f of 2.25 is going to be 2.25 squared minus 4, which is equals to 1.0625. Remember that the goal is to get to 0 here. So you have to do this a few more times, and that's why you actually program this to do in a computer, because to do it by hand it can take a while. Now notice that this one is positive. Since this is positive and this one is also gives you a positive value, so that means now this implies that now a3 is still going to be 1.5, but now b3 is going to be 2.25. So therefore p3 is going to be 1.5 plus 2.25 divided by 2, which is 1.875. And then if you evaluate this, you will see that f of 1.875 is equals to minus 0.40 48, 43, 75, and you can see how it's getting closer to 0. Uh, you should be stopping the video at the point of the calculations and check yourself using the calculator that you actually get these values. So as you can see, this is still not close to to being 0. So you do this a few more times, you'll get there after a few more steps. Now here it will check the absolute error between two successive iterations. For example, from here, if you do a P2 minus P1, you can see that the error at the beginning is pretty big. So P2 was equals to 1 point, actually P2 was equals to 2.25, and then P1 was equals to 1.5. So that would be the absolute error. While in this one, P3 minus P2, that will be 1.875 minus 2.25, and you can see that this is getting closer. So you will have to have a place where you will have to stop. This is less than 0.001 or so forth. But remember from the past, the absolute error may not be the best way to stop something, but sometimes you have no choice, you have to use this. It may be better to use the relative error, but this is what I mean by error. So you can start seeing that the distance between this is getting shorter. Now the advantages of this method is that it always converges, which is not the case for other methods. But the disadvantage is slow. So it's a slow method, and it actually has linear convergence. But if you start in the right place, the method could be a little faster. So it all depends on where you start. But it doesn't matter where you start, it's going to converge. But if you pick the right place or the right starting point, it may go a little faster. For example, so let's redo this method. So if we pick now, let's say A1 to be 1 and B1 to be 3, then P1 is going to be 1 plus 3 divided by 2, which is equals to 2. And then you can see the f of P1, which will be f of 2. It will give you a 2 squared minus 4, which is equals to 0, and then we'll be done. I mean, this pretty much never happens in real life, but it's a good to give you some motivation in this 2020. So if you start in the right place, you'll end up with the right answer right away. All right, let's do one more example. The next example is on the book too, so you can check it there. All right, so here it's asking you to show that this function has a root between 1 and 2. So therefore, it's already telling you the value for A1 should be 1, and the value for B1 should be 2. Now you should check that they have opposite signs. F of 1, it will be 1 cubed plus 4 times 1 squared minus 10, and this is negative 5, so therefore this is negative. And f of 2 is 2 squared plus 4 times 2 squared minus 10. This is equals to 14, which is positive. So therefore, yes, by the intermediate value term, you know that there exists. So I'm going to use the symbol many times for there exists a value between A1 and B1 such that f of x is equals to 0. So it's guaranteed. It may take a while, but it guarantees that it will get there. All right, so then for step 1, you can say P1 is going to be A1 plus B1 over 2, just like we did in the previous example. So it will be 1 plus 2 over 2, it will give you 1.5. Right, then f of P1 this is 18 as f of 1.5, and once you do the whole computation, this is 2.375, which this is clearly positive. So therefore, this one and this one have the same sign. So now this means now that for step 2, A2 is going to stay A1 because that one is negative, but the new B2 is going to be 1.5. And then from here, we're going to have the P2 is going to be now 1 plus 1.5 divided by 2, which is 1.25. And we do the exact same thing, f of 1.25. Once you simplify everything, this is negative 1.796, which now this is negative. And this one is also negative, so this is going to be the new A3 and so forth. Now, since the question is asking you to go all the way to an accuracy of 10 to the negative 4, you will see that you have to do a lot of steps. So if you keep going after 13 steps, which to do that by hand, it will be brutal, you will get to 10 to the negative 4. So 10 to the negative 4 here. Notice that here for the stopping criterion, we're using the actual function, because remember here we're just trying to get to 0. So remember the goal in here was to find f of x equals to 0. So in this case, it's a good idea to use the actual function. And once it gets to 0, then you're getting closer and closer to the solution. All right, so let's go to the last page. All right, the last thing we will do is theorem 2.1. It says the following. Suppose that f is a continuous function between a and b, and the f of a and f of b have opposite signs. So then the bisection method generates a sequence that approximates approximating a 0 or a root p with the following ray of convergence. So this implies that the rate of convergence, so you can see the connection with section 1.3, is O, big O of 1 over 2n, or this implies that Pn is equals to P plus big O of 1 over 2n. Now let's do an example. I believe this one is also in the book. So this is it's the same function we just did. Okay. And here we have that A1 was equals to 1 and B1 was equals to 2. And we already checked that f of 1 times f of 2 was negative, which means they have opposite sign. So the question is find n, the smallest n, to get accuracy of, let's say, 10 to the negative 3, which, remember, this is the same thing as you're saying 0.001. All right, so therefore, if we use this bound in here, so we get that b minus a over 2 to the capital N, you want it to be less than 10 to the negative 3. So this is what you want this to happen. Here, A and A1 is the same thing, just like B and B1 is the same thing. All right, so from here, we have the 1 over 2 to the n should be less than 10 to the negative 3. This also means 2 to the negative n should be less than 10 to the minus 3. Now we change from log to exponent. Sorry, from exponent to log. In base 10, we will get minus 2, so minus n log base 2, base 10 of 2 is less than negative 3. Okay, remember that log of 10 to the negative 3 is negative 3 log of 10, but log of 10 is equals to 1 since we're using base 10. You could also use base 2, but either way is give you the same answer. So from here we have the n has to be bigger than 3 over log of 2 base 10. This is equals to 9.96 or around 10 iterations. Now, if you look to the table from last page, okay, and you should look at this. When n was equals to 10, the error, which was f of p n, is equals to negative 0.01605. For n is equals to 11, this was minus 0.00799. So you can see that this is 10 to the negative 3 or close to. So you have to have at least 10 to get to this point. This is 10 to the negative 2, and this will be 10 to the negative 3. So therefore the bound is pretty accurate. All right, that's it for sections 1.3 and 2.1. The first programming homework you have to do is going to be related to the bisection method, which, as you can see, is pretty straightforward. All right, that's it.